What I'd like to do now is just take a brief 10 or 15 minutes to talk through some of the emerging trends that we see in the mining industry. I'll focus specifically on copper and cobalt, but there are many challenges that we face in the mining industry going forward. The ones that I'd like to cover today are ones, though, they've been with us for a while, but for us we see these as nearing a tipping point where we'll start to see them drive significant change in the industry. One of the benefits we have at Glencore Technology in being part of one of the world's largest mining companies is that our own operations face challenges all the time, and those challenges are mirrored across the industry. So it gives us a great insight into what our customers are looking to have to deal with in the next 5 or 10 year time horizon, and we can make sure that we're developing a product suite and evolving our product suite to be able to deal with those issues as they come through. I'd like to talk about three different changes tonight, three different aspects that are driving change in our industry. The first is the rising level of impurities in copper concentrates. Arsenic has been an issue for about 10 years now, and we're increasingly seeing issues with antimony, bismuth, fluorine and uranium. Within Glencore and within GT, we're developing a range of products that look at a better integrated smelter and refinery to be able to deal with the impurities at the best point in the flow sheet. And we've also been developing over the last 10 years some exciting hydrometallurgical techniques to deal with some impure concentrates. And Paul Boyd spoke about some of those earlier, so I'll just touch on those as well. The second thing we'll talk about, and this is closely aligned to the first issue, is ongoing global tightening of emission standards. One thing we've seen over the last 10 or 15 years, particularly in countries like China and India, is significant urbanisation and large population growth around what were once isolated processing plants and isolated smelters. And that's putting a lot more pressure on the smelting industry and the mining industry in general to reduce emissions. Zero discharge sites are really the best practice these days, and I'd like to talk a little bit specifically about SO2 and some of the things that we're doing with our technology suite to help to reduce SO2 emissions. The last thing I'll touch on is the global growth of electric vehicles. This is one, again, it's been with us for about 10 or 15 years, but with the significant spikes we've seen in fuel prices in the last 10 years, and also with the drive for decarbonisation across our industries, we also think this is something that's at a clear tipping point, and it's going to have a significant impact on copper and cobalt demand globally going forward. So firstly, I'd like to go through rising impurity levels in a little bit more detail. We started to see arsenic levels in copper concentrates increase through the 1990s, but at a very slow pace. But in about 2004, when the mining boom started in earnest, a lot of very complex ore bodies were brought to market. And in the period between 2004 to around 2007, 2008, we saw an increase in arsenic. From 2008 on, that rate of change has increased significantly. And now there's a considerable amount of arsenic that's produced annually in the world's copper concentrates. I've got some examples on the screen there. You can see some of the very high levels on recent projects. Ministro Hales in Chile, where they've got a roaster as a solution there, 4% arsenic in that concentrate, which is unsaleable to a smelter. And some of the other examples there, Chuquicamata, one of the world's largest mines, is producing a lot of arsenic in copper concentrate. And traditionally we've been able to blend that. The capacity to blend with clean concentrates is really restricted in the market at the moment, and that's a problem that will only get worse going forward. Currently we have 30% of the world's copper concentrates with arsenic levels that are too high for most of the world's smelters. Another trend that we've seen over the last 10 years is shutdown of some smelters such as La Arroya in Peru that had been able to treat those higher arsenic materials. So we get two trends there where the capacity of older smelters and more remote smelters to treat these concentrates is significantly reducing, and arsenic levels are increasing at the same time. Our belief is that we're at a tipping point now where we need to see significant infrastructure change within our smelter refinery network globally to be able to treat these impurities. And that's something that we're doing a lot of work on within Glencore technology to make sure that we can meet that demand. The next slide shows the acceleration of arsenic levels in copper concentrates. You can see the pickup there, particularly in 2012, where a lot of complex projects came on board, and that's continued to accelerate through 2018, and the prediction there to 2020 is a slight levelling, and again we're starting to see predictions now of a further increase from 2024 onwards. So that's something that's creating a significant challenge for the global industry. There are many ways that we can deal with this. When we look at the impacts on flow sheets, the first place you would deal with it is in the concentrator, but unfortunately most of the minerals that are bringing high arsenic into our concentrates are things like enegite and tennantite. And as far as a concentrator is concerned, these minerals behave very similar to chalcopyrite and chalcocite. They respond the same to the current range of mining chemicals and collectors, and it's very, very difficult to get any kind of separation in a concentrator. While we have made great strides over the last 20 years with things like the isomill, where we can get significant degree of liberation now, we still don't have the flotation technology and the flotation chemistry to be able to get a clear separation. So unfortunately for the near term, for the next 5 to 7 years at least, a lot of this arsenic will report through to the copper concentrate. As I said, historically we had been able to blend. There was a significant amount of clean concentrate around in the world. That amount of concentrate is reducing every year as the arsenic levels rise, and so blending is no longer a solution, and we need to start to look to change the infrastructure. One of the other problems that we've seen is that because we can't take the arsenic out of the concentrate, we have to export it to a smelter, and the smelters are increasingly in urban environments, and so what we're doing is we're actually bringing the arsenic problem from a remote mine site where it may be better contained to an urban centre where emissions have a much more magnified effect. So what we're looking to see in the near term then is a step change in the way that we deal with arsenic in our smelter and refinery complexes, and I'd like to touch on that in the next slide with some of the innovations that we're developing within the Glencore Technology Group and within the greater Glencore operations. One of the things we've focused a lot on in Glencore and in Glencore Technology over the last 10 years is treating arsenic in smelter dust leaching plants. Within the Glencore operations we have 5 plants. Within our own Mount Isa operations here we commissioned a plant in 2004, and that's now had 14 years of operations. These plants are all unique because the dusts that are produced are all unique. Glencore has a range of smelters that they operate. We operate a splash smelter in the Philippines, we operate an Isa smelter at Mount Isa. We get very different dusts out of both smelters, and so we have a range of flow sheets that we have developed to deal with a range of impurities. And so we have the ability to custom a solution to a different concentrate blend, and that's something that we get through our unique blend of operations and technology sales. Our belief is that the world's best practice for arsenic fixation is vitrification in slags, and that's something that we're developing at the moment in conjunction with some of our partners within Glencore, and it's a technology we'll be looking to offer globally in the very near term. The traditional practice of fixing is a ferric arsenate, while it was world's best practice 5 or 6 years ago, really increasingly globally is not an acceptable disposal method anymore, and so we need to look at something that is a lot more stable and a lot more sustainable. One of the advantages that we have within our own product suite is the ISOSmelt technology. The table on the right-hand side of the slide there shows the world's the world's more popular copper smelting technologies. The flash and the ISOSmelt tend to dominate the market these days. One of the unique things about the ISOSmelt is it does concentrate the majority of the arsenic in a single stream in the ISOSmelt dust, and that allows us to focus on a very concentrated stream of arsenic and get a very effective bleed from the smelter. So when we develop a treatment flow sheet for arsenic, an ISOSmelt dust is a perfect feed because of the ability to take the arsenic out of a single point and have a quite compact plant and quite a simple flow sheet. The photograph on the bottom right hand of the slide there shows the dust leaching plant at Mount Isa. It is a leaching plant. We use acid from the weak acid effluent from the acid plant, which also contains arsenic. We use that to leach the dust, and then we fix the dust in that plant there as a ferric arsenate using lime and limestone precipitation. One of the unique things about the flow sheet at Mount Isa is we recover the copper through a metathesis reaction, where we cement it back onto the copper concentrate and feed it back to the smelter. So that's a very, very low cost way of recycling copper to the smelter, and a very effective bleed of arsenic from the dust stream. The next option, and this is one that Paul touched on, is direct leaching of these high arsenic copper concentrates. Glencore has done a lot of work in Africa in the last few years, and we've very successfully recently commissioned an Albion leaching plant there. You can see the photograph in the slide of the first copper that was produced in our plant in Africa, and this is really a significant step forward for the copper industry globally. Copper hydrometallurgy has been a dream of the industry for a long time. It's one though that's seen 7 or 8 very well publicised starts that haven't been successful. We believe that the combination of a very simple Albion process oxidative leach with conventional SXEW will give the copper industry the hydromet solution that it's finally looking for. We can get over 99% recovery of copper from copper concentrates and a very effective separation of arsenic. One of the good advantages of the hydromet plants is that you can build them at the mine. You're not exporting an arsenic-rich concentrate to a smelter, and so we get around the problem of concentrating arsenic in urban areas as well. The other technology that Glencore had developed internally is a sodium sulphide-based leaching process named the Tuong process. That's one that we're currently continuing to look at with a partner, Core Resources. This is a technology where we can actually generate the sodium sulphide in situ within the leaching circuit rather than have to add sodium sulphide from an external source. It's an emerging technology that we think in the next 10 years can have a significant impact in trying to selectively remove arsenic out of copper concentrates as well. I'll move on to the second trend that we see starting to put increasing pressure on the industry, and this is SO2 emissions around smelters. There's been a tightening of SO2 emission levels around smelters. We've seen this particularly in the last 10 years, where financing organisations globally, such as the World Bank, the International Finance Corporation, have every 5 years or so tightened the SO2 restrictions around plants that they're prepared to lend to. You can see on the slide there the current IFC World Bank guidelines of a 20 micrograms per cubic metre over a 10-minute period and 125 micrograms per cubic metre over 24 hours. These are extremely stringent and they require modernisation of a lot of the existing smelter networks around the world, and any new smelting technology needs to have a very inherently safe design, and a design that is able to capture these days over 99.8% of the SO2 that's emitted, and that would be considered world's best practice. Now, the Isosmelt vessel is a primary smelting vessel, and primary SO2 gas capture is something where the technology is quite advanced. Acid plants are common on smelters. This is a trend we saw beginning in the 1980s really start to gain pace, and most smelters around the world now have a metallurgical acid plant capturing gas from the primary gas streams. The remaining problem though is fugitive emissions, and these are emissions where you'll get puffing around furnace ports, and these can account for about 5 to 10% of SO2 emissions around smelters. In a modern smelter, less than that, but in a lot of the traditional smelting network globally, you can get that much SO2 loss, and it is as a low-level gas. It's very difficult to capture, very expensive to treat. You can see in the photograph on the bottom right-hand side of the screen, this is a pot movement down a converter aisle, and this is a very common source of fugitive emissions in smelters at the moment. The main issue is in most copper smelters these days is emissions around the Pearce-Smith converters. So Pearsmith converting accounts for about 80% of converting worldwide. And because the Pearsmith converter is a rotating furnace, it's extremely difficult to seal around the port of the furnace. While we have seen some very good advances in hood technology and capture technology over the recent decade, it's still not sufficient to be able to capture the SO2 to the levels that we can see financing organisations globally moving to. So there is a need for a new converting technology. Flash converting has been around for a while, but it is a very expensive technology. It is very complex and not ideal for emerging countries where the workforce and the level of training and skills may not be up to operating such a complex and expensive unit operation. Because we have the TSL furnace that we've developed for Isosmelt as a very simple, very low-cost unit operation, we've done a lot of work to adapt that for continuous converting, and we have the first of these vessels being constructed at a client site in Africa at the moment, and that will be commissioned later in the year. The benefit of continuous converting, it's much easier to capture the SO2. You get a very concentrated SO2 stream, which means that you can do more with the gas in terms of feeding it through to an acid plant. So that's something that we see a very bright future for in our technology suite going forward, is the IsoConvert technology, which is continuous converting of matte from the Isosmelt furnace. To complement that technology, we've also been doing a lot of work with fugitive emissions around the feed ports of our TSL furnaces. You can see in this slide here an induced draft feed port. This is something that we've developed over the last 5 years and something that we commissioned successfully at Mount Isa in 2006. This device uses a Coanda surface to trap gas within the furnace and make sure that SO2 is directed to the off-gas system and captured effectively through the ESP system. It's been a very successful technology. We can use it to seal off around our feed port and around our lance port, and this is the next great advance that we have for the Isosmelt and the IsoConvert furnaces for improved SO2 capture. Also has the secondary benefit of reducing arsenic emissions through those ports and moves our technology suite ahead of the curve and into what we believe is world's best practice. The final trend I'd just like to touch on is the increasing use of electric vehicles globally. We've seen this emerge in particular in the last 5 years, and where we've seen elevated fuel prices and we've seen a lot of social pressure on decarbonisation. The automotive manufacturers globally have been slow to respond, but we have seen some disruptive producers emerge, Tesla as a very good example. And the amount of electric vehicle batteries produced is increasing exponentially at the moment. Predominantly the major battery that's used in electric vehicles is a nickel manganese cobalt cathode battery, lithium ion style battery. One of the keys to these batteries is cobalt, because to get a very deep cycle life out of these batteries you need cobalt. A lot of producers have looked at nickel heavy blends, cobalt light blends in the last 5 or 6 years, but they haven't been able to consistently deliver the 10 to 30,000 cycles that an electric vehicle battery needs to match the life of a car. You need to expect the batteries to last for 10 or 15 years because that's what you'd expect out of an expensive motor car, and you need cobalt in the battery to be able to achieve that. What that's led to is a significant spike in cobalt prices globally. That's something that we've seen over the last year. We expect that trend to continue in the very near term, and we would expect that to continue easily over the next decade. One of the reasons we see elevated cobalt prices going forward is cobalt is predominantly produced as a byproduct from the production of nickel and the production of copper. There are very few mines globally, and there are very few that are slated for future development that specifically produce cobalt. Because of that, it's very hard for mines to ramp up, and it's very hard for existing producers to increase their cobalt output when their primary output is another metal. That means that the demand for cobalt will continue to increase, but production levels will stay fairly flat, and we expect fairly flat growth in cobalt production. Because of that, within the Glencore group, we're doing a lot to improve recoveries in our operations, and we're developing a lot of technology around cobalt production, some of which I'll touch on in the next few slides. This slide shows cobalt production globally in 2016. Cobalt comes from three main sources: nickel cobalt sulfide concentrates, and within the Glencore group we have mines in Canada that produce significant quantities of nickel cobalt sulfide concentrates. Cobalt from nickel laterites. Now, nickel laterites have had a very difficult history. There haven't been many truly economically successful operations. Glencore operates the Murrin operation in Western Australia, and we have experience with that technology. And one of the emerging sources that we have a lot of faith in the future is the copper oxide and cobalt oxide deposits in Africa. There are significant oxide resources in Africa, enough to meet future cobalt demand for a significant period of time, but in quite challenging regions. You can see from the graph on the right-hand side there, 50% of the world's cobalt currently comes from the DRC, and that has quite significant geopolitical challenges. It's a difficult area to operate, and so that puts significant risk around cobalt production. Glencore has two large mines in the region, and I'll touch on some of the output from those mines shortly. The other potential source that we see for cobalt production is recovery from low-grade copper-cobalt middlings, and we'll just touch on that towards the end of the presentation. The next slide summarises some of Glencore's global cobalt production. We produced 27,000 tonnes of cobalt last year. We're planning to produce about 60,000 tonnes towards the end of this year, and that's a significant expansion in our cobalt production, predominantly through our African assets, through some expansions there. There's a list of Glencore's operations. We have operations in Canada producing sulfide, nickel laterite operations in West Australia here in Australia, and we have two quite large copper cobalt mines in Africa. So within the group we have experience across a whole range of treatment methods for copper cobalt, ranging from high pressure autoclaves in the laterite treatment through to direct leaching and cobalt oxide, cobalt carbonate precipitation within our African operations. We also run the world's largest cobalt nickel refinery at Nikkelverk in Norway, and we're experienced there with direct copper electrowinning as well. Sorry, direct cobalt electrowinning. I'll speak to one of the operations that we're currently upgrading in the Democratic Republic of the Congo at the moment. This is our Katanga operation. On the left-hand side of the screen there you can see the existing flow sheet that we had at Katanga, where we had a combined oxide and sulfide flotation circuit producing copper as SXEW metal and producing cobalt as a cobalt hydroxide product. We're expanding that operation at the moment from about 120 to about 350,000 tonnes of copper, and because of the value of cobalt we're looking to improve cobalt and copper recovery. For that reason we've removed the oxide flotation step from the circuit and we've converted the plant to a direct leach. So while that has significant operating cost challenges because of all of the mineralogy that goes through the leach circuit, the increased revenue more than compensates for that, and it does simplify the flow sheet. This plant is being commissioned at the moment in the DRC and being ramped up, and we expect it to hit full production sometime in the first quarter of next year. At the back end of the flow sheet you can see on the right hand side we produce cobalt as a cobalt hydroxide, and this is done in many operations around the world. Traditionally this is done with a magnesium oxide feed, and magnesium oxide is quite an expensive reagent and leads to quite a high cost production method. Within the Glencore group we've been developing a technology to significantly reduce the costs that I'll cover in the next slide. And this is something we've been testing in several operations recently. What we've found is that we can replace the high-cost magnesium oxide with low-cost lime and part of the neutralisation with limestone. What this gives us is a blend of cobalt oxide, cobalt hydroxide and gypsum. But by controlling the conditions properly and by favouring gypsum growth, we can get quite a significant size difference between the gypsum and the cobalt product. And through simple separation through a cyclone, we can produce a 45 to 50% cobalt product consistent with what will be produced in the magnesium oxide circuit, and separate a gypsum product out at about a third of the cost of operating that circuit. So this is a significant step forward and one that we've developed specifically within our operations over the last 2 or 3 years, and something that we're quite happy to work with our external clients on. The next aspect of improved cobalt recovery that I'll discuss is albion process. I won't go into this in much detail. Paul spoke to that earlier. But one of the things that we do see is people throw a lot of cobalt away in the form of low-grade copper-cobalt middlings in many flow sheets around the world. Probably 5 or 6 years ago, these materials weren't economic to treat, but with the cobalt price as it is these days, and with the prices that we see going forward, it's very viable now to start to treat these middlings. The albion process is an ideal circuit because of the low capital cost and the very simple process. It's something that can be retrofitted to an existing concentrator to recover a copper-cobalt bleed stream. We can treat that easily in the fine grind oxidative leach. And with the high-grade oxide technology I just mentioned, we can use that to now produce a high-grade copper and a high-grade cobalt intermediate in a very low-cost circuit. You do also have the operation of SXEW, or the option of SXEW for copper production, but with the combination of that and oxide precipitation, we now have a very, very low-cost option for exploiting cobalt from middling streams. So that wraps up the short discussion about some of the emerging trends that we're seeing. We'd be very happy to talk to any of our clients at any time about some challenges that you may have. We have a very innovative group within our Glencore technology team and a great depth of experience there, and we're very proud of our abilities as problem solvers. So please, if anyone has a problem, we would welcome you to contact us, and we'd love to work with you to solve that.